Okay, welcome to the second talk of the afternoon, where Divya Rani will be talking to us about building a code search engine. You can start when ready.
Sure, thank you. Hello everyone, this is Divya, and today in this talk, I'll be talking about how to build a core search engine using natural language processing. Brief about agenda. So we'll be talking about what is NLP, and also we'll go over the whole workflow regarding how we'll collect the data, pre-process, cluster, and extract the methods. And after that, we will see a short demo on how to create a small code search engine. Now, coming to natural language processing, what exactly it is. So, natural language processing refers to the branch of artificial intelligence that gives machines the ability to read, understand, and derive meaning from human languages. In our case, we will leveraging NLP to extract meaning out of docs and functions and try to get similar methods. Now, NLP, there are various Python packages that support NLP. Today, in the demo, we'll be actually seeing some of them. So there are three Python packages that we'll be discussing. One is GenSim, which stands for Generate Similar. It is actually used for a topic matching algorithm, which is useful for high cardinality keywords. So suppose let's say we have a collection of books and we have to categorize them into different buckets. Let's say mystery and thriller, and one is comedy. Now, obviously, mystery and thriller will go into a different bucket, and comedy will go into a separate bucket. This is where the topic matching algorithm comes in. It helps to categorize different things into buckets based on how similar the keywords are. Now we also have natural language toolkit and scikit-learn. Both are used to implement machine learning algorithms. But scikit-learn provides wide range of algorithms out of the box. We don't need to implement it from scratch. With NLTK, it is kind of biased towards more on data processing side. We can still implement some libraries using using NLTK, and it does provide a good opportunity to do some fine tuning there. This is a motivating example of exactly what we are looking for. Now, this is a split library. Here, we use in this case, we have a text called hello world, and we'll be using a split function to split the sentences based on the delimiter, which is here a comma. Now we can see here the C Python. It has the standard library. It provides a split functionality, and also we have the string utils. Similarly, in other languages as well, we will have some split method, right? So what we are looking for ideally is like given a tool, let's say the code search engine, we provide a query. Suppose let's say split a sentence, and then we will get different methods across different languages as output. So that's what we are looking for, and we will get to know how we can build such kind of tool. So before going forward, we need to have some kind of corpus with us, that is data across different libraries. So this is where the data collection comes in. Now, with similar libraries, methods, and documentation, we have to pass different methods, documentation, and we will kind of follow a black box approach, as in it doesn't matter what language it is, as long as it's similar. It as long as providing a similar method, it will be part of the corpus. Now, how to extract this data? So this is where the BigQuery API comes in. BigQuery API provides, it has a large corpus of a GitHub repository through which we can get the source code files, basically path of all the source code files. And then those paths can be used as an input to this library called PyGitHub. With PyGitHub, we given a path of a file, it will extract all the content of it, and then we will have the raw format of data which we can use in order to build the tool. So with BigQuery API, we have to use a SQL query, and this is how the query would look. In this case, we can see this particular file which will be used in order to extract the data, and we can add the repo name here. Now, given what kind of similar methods we want, or exactly what repository we want to use, this is something that is subjective. And again, depending on like what we don't want, we can exclude some of the files as well. Now, after extracting the raw data, how it would look like. Now, this is one of the example of a function called post tag. And in this case, we see there this documentation and also this method signature. Now, this documentation provides a lot of information about this particular method, which can obviously use to find what exactly this method is for. And similarly, other libraries might provide the same method with their documentation. And based on that, with this documentation, we can calculate the semantic similarity. So, for example, let's say this is a postdoc, this is from a different library, library one. And from library two, we have a different method which provides similar functionality and have a kind of similar documentation. Now, since the documentation is similar, not exactly word to word, but the semantic meaning is similar, then we can leverage it to get the collection of the similar libraries there. Coming to the data pre-processing part. So once we get the raw data, we cannot use it as is. We need to pre-process it, clean it. So this is where some of the steps comes in. First is tokenization. So tokenization breaks down the text into smaller units like word or phrases to make it easier to process. Then we have stop word removal, which remove common like words like the, is, and that don't convey much meaning, and it will just add noise to the data. So this is where we need to remove the stop words. Then there's lemmatization. So it helps standardize different forms of word that convey the same meaning. For example, let's say we have three words like run, running, ran, but all of them have the same meaning. So using lemmatization, it can get reduced to its basic form, which is run. Similar to, let's say, eat, ate, or eating, these all can reduce to the basic form, which will be eat. Coming to bag of words. Now, bag of words, we can think of it as something like a hash map. So this will actually store the frequency of all the words which are occurring in the documents, and it would be used further by the clustering algorithm to figure out which word is more important in the document. So we will see the examples of all of them. So this is how this is how, if we tokenize a sentence, this is how it will look like. In this case, we are using the NLTK library, and you're using the word tokenize method here. And in this case, once we have this text and it's just splitting them into simple words, and we also see some punctuations here and there. These are actually part of the stop words as well, and this can further be refined. Now this is the stop word removal. So we have this original text, and after the tokenization, this is how it would look like in the form of list. And once we remove the stop words, this is the resultant list. Again, in here, we see some punctuation marks here and there, which can be again removed through some libraries. Now, lemmatization. So here's the original text. And after that, when we split them into different words, this is the token, and these are the lemmatized words. So as you can see, foxes become fox, R becomes V, running becomes run. So this is what lemmatization do. Coming to the bag of words. Now in bag of words, we have this corpus here. And as you can see, this is more like a hash map with the number of, basically the frequency. So in this case, for sentence one, the occurs twice. In this case, we can see it's two, cat is one, and sat is one. So this is like the frequency of all the words that had occurred in the corpus. Now we will focus on the data clustering part, where we will discuss about different algorithms which we will be using to extract the semantic meaning. So First is latent display allocation. Now, it is one of the most popular topic modeling methods, and in this case, each document is made of various words. So, all the words which are present in a document, it is again divided into buckets based on which bucket it is semantic closer to. So, a layman example would be, suppose you have various photographs, documents with captions, and you want to display them in a gallery. So, you decide to categorize the photographs on various topics, based on which you will create different sections in your gallery. Now we can decide, like, we want to create two sections, let's say nature and city. Naturally, the classification isn't so clear, as some photographs with city have trees and flowers, while nature ones might have buildings on it. So we decide to assign the photographs with only which only have nature or city elements in them. So their respective categories. Uh, and then we notice that a lot of photographs in nature have word tree in their caption. And so in this way, we conclude that the word tree and topic nature must be closely related. Now, let's say if we pick the word building and check how many photographs are in nature, because they have word building in their caption, we don't find many. And now we are less sure about building belonging to the topic nature and associate it more strongly with the topic city. So let's say we then take a photograph which has the caption called "the trees in front of building and behind a car" and see that it is in the category nature currently. So yeah, we then choose the word tree and we'll calculate the first probability. That is basically other words in the caption are in building, are building and car. Most photographs have captions with building or car in it are in city. So we get a low probability which indicates that the picture might not belong in the nature category. So this is how basically the latent racial allocation works. It will try to make several passes until unless it gets all the words into correct topics. This is the example code. In this case, again, here we see the corpus, and we will see the whole code in the demo, and we are pre-processing it. So we are pre-processing, basically we are cleaning the document. And after that, we see a dictionary. So this will contain all the unique words present in the corpus. And then we are creating a bag of words, which is again the frequency of the words occurring in the documents. And we are storing it in the form of pair of ID and frequency. Now we see this LDA model, see this LDA multi-core. And in this, we see the number of topics 3. Here we're deciding that we want 3 different topics. And then we see ID to word parameter, which is crucial because it maps between the word IDs and the actual words. So the book corpus is, so in the bag of word corpus, we store the elements in form of ID and frequency, and we need some kind of relation so that we can map the words to it. And this is where dictionary comes into picture. And then we have passes. So the passes parameter determines how many times the LD algorithm iterate over the entire corpus. This is important because LD is an iterative algorithm that refines its estimates with each pass. More passes can lead to better topic coherence and also increase the computation time. So it's all about finding the balance between model quality and computational efficiency. Now here we see this graph, and this is actually from this tool called PyLDAViz. Now this left panel shows some topics as bubbles. A couple things to note here is the relative size of bubbles indicate the relative prevalence. That is, the larger the bubble, the more prevalent the topic is. And a good clustering model is the one that minimizes the intra-cluster distance and maximizes the inter-cluster distance. So in this case, based on the distance, we can see the LDA perfectly seems to achieve that. Other than that, we have something called relevance metric, and it's actually a tunable parameter, and it is introduced to rank the tokens within the topic. So the default value of this metric is 1, and it is equivalent to ranking the tokens solely based on the corpus-wide word frequency. Now coming to TF-IDF, which stands for term frequency inverse document frequency. With TF-IDF, it determines how important a particular word is in the document. So high term frequency means the term appears frequently in the specific document we are analyzing. This suggests that the term is important for this particular document. Now low document frequency, which leads to high IDF. This term appears in few documents across the entire corpus. This suggests that term is rare and potentially more meaningful when it does appear. With TF-IDF, it has various use case. First is information retrieval. So various of TF-IDF variations of TF-IDF are used as waiting factory by search engines to help understand the relevance of a page to use a search query. And TF-IDF can help quantify what a document is about, which is a central question in text mining as well. Well, this is the overall formula. That is TF, the number of times the term appears in the document. This is basically multiplication of two different algorithms. And one is inverse document frequency. So number of the documents in the corpus and number of documents in the corpus containing that term. And we take the log of this. Now, cosine similarity. So cosine similarity will actually tell uh, how similar two different documentation are. It's actually a mathematical metric used to measure the similarity between two vectors in a multidimensional space. So, for example, let's say me and my friends, we have three books, and I rated all those three books 5, 3, 4 respectively, and my friend rated it 4 to 4. Now, someone can ask how closely these ratings are related, and we can say something similar like, okay, it's closely related, but not as much. But how can we quantify it? Like how 534 and 424, which are the ratings, are related to each other, and how similar are they? This is where cosine similarity comes in. The cosine similarity will return a value between -1 and 1, and a value closer to 1 indicates great similarity in our and in this case, basically how TF-IDF and cosine similarity, how both of them work together is TF-IDF is just a way to measure the importance of tokens in text. Uh, it is just a very common way to turn a document into a list of numbers. We can call it vectors. And cosine similarity will actually act upon those vectors. So to compute cosine similarity, we need two document vectors. The vector represents each unique term with an index, and that value of that index is some measure of how important that term is to the document. So overall, how exactly we will go for the similar method extraction is we will use latent Dirichlet allocation model to do the topic modeling approach. For this, we'll use the GenSim, and further, then we will use the weighted TF-IDF score and cosine similarity to compute the semantic similarity. Now we will be looking at the demo of how these algorithms that we just learned and how we can use it to build a small code search engine. So we will go one by one. We'll first start with LDA, which is a latent Dirichlet allocation. And we'll first go through the main function here and see what is going on. Before that, regarding my setup, so these are the packages that I've installed: NumPy, NLTK, GenSim. This is for the visualization, and these are the libraries. So,
Can you increase the font size a bit? It's a bit small here. Thank you. That's much better.
Thank you. So, in this case, first we need to download the libraries, and these are the ones that we are downloading. So, in this case, we see something. This library. It is actually used to detect the sentence boundaries, and it is used for tokenization. So, if we have a sentence which stops at somewhere, let's say punctuation, this is the library which will be able to which will help us to identify that. We have stop words. Earlier, we learned what stop words are, and this will helpful in removing all the noise. Now we see something called WordNet. Now this is actually a dictionary, and we'll talk about why exactly it is used. This is our corpus, and this is a collection of books of different genres. Now we need to do the pre-processing. So if we go to pre-processing, we see we are tokenizing the words, that is breaking down the sentences into smaller words. And we see something called lematizer. Now lematizer actually use a lexical dictionary in order to stem the sentences. So what I mean by that is, like, if I use something like sorry, if I have something like eight, how does the limitizer will know like it relates to eat? So it needs to look at a dictionary, and this is where the wordnets comes in the picture. After that, we are collecting all the distinct stop words that we need to remove, and we are collecting all the terms here. So we are checking if the token uh, is not in stop words and is not alphanumeric, then we limitize it. Now coming to this, we are creating a dictionary. After we get all the unique words, we are creating a dictionary out of it. And then we are collecting a pair of ID and frequency here. This is the same screenshot that we saw earlier. And after we actually train the model, in here you must be seeing I've added workers too. So this is basically I've employed a multiprocessing package here so that it will be done faster. Please keep in mind that the more number of passes I make, the longer it will take. Other than that, now we can once we have the documents here, just a second. Yeah. We can go through the LDA model once it goes through it and print all the topics. So we will just run this tool and see what is the result. Just a second. These are warning of the deadlocks because I added a number of workers, but we can ignore them. So in this case, we are seeing so it is going through all the documents which are mentioned here in the corpus, and it is trying to divide them into three categories, three topics, and it is calculating the score to which topic this particular document belongs to, as we can see. Yeah. So in this case, for example, this narrative nonfiction detailing the life this last document, this belongs to topic 2, because again we see that it's much closer because of the higher value, and this is how all this corpus will be segregated on based on three different topics. And here we can see what those three different topics are and what are the collection of the keywords here. So, for example, topic 0 is detective, set, life, dark, Victorian, and covers, right? And we see that in this case, a thrilling mystery, it has higher score in topic 0, which indicates that this is correct. Same, we are seeing something like an epic fantasy adventure. This also is in top. This is also in topic. This is in topic 1. So topic 1, we see it's like fantasy, science, there's world and all. So in this case, it's also relating closer to this particular topic, an epic fantasy adventure. Now we'll see other algorithm, which is TF-IDF here. In this case, we again go to the mun function. We do the similar, download the libraries, and this is again a corpus of the same book description that we saw earlier. And we will compute the TF-IDF of this particular corpus. We again go to the pre-process doc. And here we see something else. We see that we are using something called stemmer. Now, what exactly is stemming? So, there's a difference between stemming and lemmatization. Stemming as well strips the suffix of a particular word, but it could also result to a non-word as well, which means that again we can see here the results. If the university is there, it's possible that it will stem it and it can become something like universe without any, which doesn't mean anything. So why someone would use stemming but not lemmatization? With lemmatization, with for each word we have to do a lookup in the dictionary, which can be slow. But with stemming, that is not the case. Again, it could lead to more inaccurate results. But again, these are like most of the pros and cons, and to keep a balance, if we don't care about the like absolutely accurate result, stemmer can be used. But if we want to have totally accurate result, then we can use the limmatization. In this case, we after pre-processing, we again go to we compare that we compute the term frequency and inverse document frequency. So here we see we are just using the basic function here, like number of times the term appears in document, this basic math here. And the same formula we saw earlier in the screenshot we are using for the compute IDF. Now, once we get the matrix of this, we will do a cosine similarity on top of it, uh, basically to compare how each of these documents are being matched to each other, how similar let's say this first sentence is to the second sentence. And also, we will be actually passing in a query and see which particular, let's say, book this particular query will be closer to. So we can run this. And so now we have with the query and book one, it seems that the query and book one is much similar. So we will see what the query is. A mystery novel set in modern day New York with a female detective. And we see what the book one is. It's a thrilling mystery set in Victoria, London, uncover dark secrets. So in this case, we see that semantically with the query, book one is much more similar. Similarly, in this case, we also see it has the same with book two also it's being matched. And for other books, the score is a bit lower. So this is the TF IDF along with the cosine similarity. Now we will actually look at the similar methods. Basically, we will see how we can use all these algorithms and extract similar methods. So in this case, we have seen this earlier before, and we have some code snippets. In the corpus is a bit low here, so the score might be here and there. But we have here 6 functions and along with some documentation. We will do the pre-processing normally. Here, I think we are using the limmatization just so that we can get accurate results. And after that, we will perform the LDA, which is again the topic modeling approach. Now, in this case, we want to combine the results of both the LDA and the TF-IDF. One more thing to mention here, we are using scikit-learn, and we are directly using this function TF-IDF vectorizer. Earlier, we implemented from the scratch, but in this case, with sklearn, we can actually directly use it, and it will be doing the same mathematical operation underneath. So yeah, in this case, we perform the LDA, we print it. And now we are performing the TF-IDF vectorizer and fit transform. Basically, it's performing the calculation. And then we are performing cosine similarity. We see that we are using the same matrix. The reason being, we want to also calculate how all of these snippets are relating to each other. Basically, how relatable is calculate average to calculate mean. So that also we want to calculate. And other than that, we also have a query. So in this case, the query will be calculate the average of numbers. And if we go to search similar function, we will are doing the similar thing, basically using the TF-IDF and then getting the cosine similarity. Now, in this case, one thing that might look confusing is exactly this particular line. So once we have the cosine similarity with us, in this case, with the find similar snippets, we actually can provide the query index. So where the query index is coming from, in this case, we are seeing the code snippets, this particular one, that is the first value. We are providing that. And then we are calculating how it is actually relating to all of these. And once we get that similarity, we will actually sort the similarity in descending order. And after that, we will exclude. So we are actually taking from one and then to tell the number of methods that we want, and that's what the result will get returned. Yeah, in this case, we can actually try running and see what would be the output here. Yeah. So in this, like with all the methods we are seeing, we actually asked for two topics with the TF, IDF. So this is the way they were performing the LEA, and number of topics that we provided were two. So that's why we are seeing two topics here. And the two topics we'll see how exactly like similar the methods could be. So the similar the keywords would be. So in this case, number, list, item, search, average, performs, and data and mean. For other, it's again array, item list, perform, search, ascending, order, maximum, sort. So with the topic one, it's more looking much more like this is for sorting, for ascending or descending, and for the topic zero, it looks like it is more for average and mean. Now we our query was to calculate the average of numbers. So we will see what would the output of that. So with calculate the average of numbers, in this case, it got the given there's too much semantic similarity with the first document. It got that, and it got the second document as well, which is compute mean. We can see the score. This is again the score is much higher for this one, and for compute mean the score is a bit lower. Now with the cosine similarities, uh, this particular function that I was trying to explain. So this is the output of the cosine similarities. And let's say if I chose the first document here, first which I chose the first document here, which was def calculate average numbers. So this is what it gave as a result. Now this particular values, these are related to the snippets that we have added here. So for example, this 0.192575, this actually relates to compute mean, and 0.0708, this will actually relate to find max. So this is how the cosine similarity matrix would look like. Now we would actually want the indexes so that we can grab the snippets from here. So this is where just like, yeah, this is where once we reverse sort it and then we get the index, and then we actually return the index and we get the result. Now going back, I'll just stop sharing. So this is the whole overall workflow of the extractor framework. First, we do a raw data extraction. Then we do some data refinement. After that, we do some clustering based on the different algorithms that we saw today. And then we extract the results that come out of these documents. So that's all I had, everyone. Thank you.
Right. Thank you very much. Are there any questions? Right. It doesn't look like that. Okay. Thank you very much for the talk. And let us thank the speaker again.